Now let's consider entropy's origins in the Industrial Revolution. So far we've largely been talking about entropy in a fairly theoretical way. We've made reference to Boltzmann and him thinking about what molecules might be doing and what states they're in. But actually it was technology and the real drive to improve technology in the Industrial Revolution that made all the difference with entropy. As we can see on the slide, there's a picture of a steam train there, but as we're going to see, this wasn't really the original problem that got everybody started with entropy. So actually you turn the clock back to the 18th century, and the really important engines there were these piston and cylinder steam engines to pump water out of mines and indeed to drive ships. And so this really represented the beginning of technology in the Industrial Revolution in the UK. And so this is where a lot of the early inquiry went. And they're called heat engines because ultimately they were generating heat from burning coal typically. And that heat, the idea was to get some kind of useful work out of it. So like pumping, for example, pumping water out of mines and driving engines, some kind of useful mechanical work from this heat that was generated from coal. And so the picture there illustrates the 1712 steam engine from Thomas Newcomen. So this really was perhaps the first really successful steam engine. And so ultimately, of course, the energy starts off in the form of chemical energy in coal, and as the heat energy liberated boiled water into steam, this could push a piston in a cylinder, and actually condensing the steam back into liquid water caused a massive drop in pressure, and actually this could also do mechanical work, pulling the piston back. So really this is all about energy conversion from one form into another, essentially heat into useful mechanical purposes. And of course later on, of course these days we're using heat energy ultimately to generate electricity, similar sort of principle. And so these early steam engines, on the other hand, they really were extremely inefficient. And so, yes, they could do useful mechanical work, but actually most of the heat that was produced was not converted into work. And we see these initial absolutely minuscule figures for the percentage efficiency. So that's just 0.5% of the heat energy being converted into the mechanical work. But there were later refinements in the technology, notably James Watt, later in the 18th century, producing a more efficient pumping engine. But even so, it wasn't achieving brilliant efficiencies. I mean, they still didn't exceed 5%, so efficiency was still a major issue. So efficiencies did improve through the 19th century, but of course that got scientists wondering, how efficient could you be? Was there a theoretical limit to this efficiency? Could a machine be 100% efficient, converting heat energy into work energy? And so there's a sort of a family connection here we're going to see in a moment, but just to preface this with a comment that ideas of conservation of energy can be traced back to Leibniz early in the 17th century with the first law of thermodynamics, which really states the conservation of energy. And so later on we get to see this family connection early in the 19th century with Carnot developing his theorem that ultimately there was an inevitable dissipation of energy that would make, for example, a perpetual motion machine impossible. And so he really had in mind this idea, the inevitable friction that would take place in a machine and the vibrations that were always found, and how this was tantamount to a loss of energy. So essentially he was able to rule out perpetual motion machines, and that's Lazare pictured at the top. But actually it was his son, Sadi Carnot, who made really the more significant point extending this theory. So he made the point that even if a machine could be made absolutely ideally, in the sense that there's no friction whatsoever, no vibration whatsoever, despite all that, you still couldn't get 100% efficiency in the conversion of heat energy into mechanical energy. And so Sadi Carnot's great breakthrough was actually determining what the maximum theoretical efficiency would be, and using his model he ended up with a very surprising result, and that it only depended on a ratio of temperatures of the so-called hot and cold reservoirs. So the hot reservoir, this is ultimately the heat source. So for example, if you're burning coal, that would generate a lot of heat, that would represent the high energy end of the machine, and then ultimately as combustion products were exhausted and go out into the atmosphere, that temperature would represent the low energy end of the machine. And so now to look at Clausius. And Clausius, in this pursuit of understanding about efficiencies, he started working towards this notion of entropy, which was very closely related to this idea of efficiency, as we're going to see. And so actually I've mentioned Boltzmann before, but really it's Clausius's name which is actually most associated with entropy. So Clausius is the name that we most associate with entropy on the macroscopic scale. So at the scale where we can measure things directly, like heat and temperature, Clausius made the important breakthroughs. And so really he formed a mathematical basis of what we mean by entropy. And so he was looking really at heat and work, the relationship, the equivalence between them. And so he came up with this definition of entropy, looking at a heat change divided by the temperature. And so as you can visualize this, if you put a certain amount of heat into a system, then you can imagine that heat energy having more of a, if you like, a disorganizing effect if a system is at extremely low temperature compared to if it's already very hot. And so I think we mentioned before the ideas of an analogy between, say, shouting in a crowded bar versus shouting in a quiet library. So while there's already a lot of ambient noise in a bar, adding a bit more energy through the form of shouting doesn't make a huge amount of difference, but actually makes a very significant difference in a very quiet environment. And so Clausius was looking very carefully at heat engines and the idea that there can be a cycle, that's to say a number of processes which returns the heat engine back to its original state. And so ultimately in these early researches he saw Q over T, this quantity of heat energy put in divided by the temperature of the system, ideally, well not ideally, but in practice was producing a positive value on a complete loop around the cycle. And we'll see this actually mirrors what we later understand to be the second law of thermodynamics about entropy increasing. And so later on he realized that he could visualize a circumstance when it wouldn't have to be a positive value. It could in theory be zero, this Q over T quantity going round a cycle, but there was absolutely no way it could be negative. And so again we meet this concept that the entropy increase can be zero under very carefully specified conditions. These are equilibrium conditions. And so ultimately when we're looking at the macroscopic scale, an overall process must have a positive entropy change if it's happening spontaneously, and the greatest extent to which you can reduce this entropy would actually be just to the point of no change, zero change at equilibrium. So at equilibrium nothing appears to be changing. And so this word entropy has built into it, in the sort of etymology of the word, or at least it seems to be implied in the Greek, the idea of an intrinsic direction. So this I think links somewhat to the arrow of time being an intrinsic direction. And because of Clausius's studies of heat and work and the equivalence between them and the use of entropy in this context, he liked the idea of the word entropy sounding a bit like energy. as it was concerned with the so-called quality of the energy. And this is something we will return to. So energy is quite a generic idea. Energy can have lots of different possible forms, and we can also associate quality with them. And so we regard heat as a fairly low quality, sort of disordered kind of energy. And in fact, mechanical work, so moving something, let's say, against a force, this can be very much highly ordered energy and therefore high quality. And so entropy actually talks about the quality of energy. So again, he's trying to make the term look rather like energy. Nobody really knows why the letter S is given for entropy, and some people have speculated that Clausius might be giving a nod to Carnot with all of his important developments. Now we're going to look at the Carnot cycle. So this was something Carnot invented to tackle this problem of the maximum possible efficiency that you could have in a heat engine. Now there's nothing meant to be realistic about this, but he's just looking at a kind of idealised case, an idealised model. It's not in any sense meant to depict a real engine. And so what he did in this kind of theoretical treatment was that he produced a cycle in this heat engine that had 4 different stages. And so we'll have a look at those in turn here. And you have a so-called working fluid, and the working fluid is the gas in the movable piston. And so as a working fluid, it's the thing which expands and contracts and does the work. It's associated with the moving parts. And so if we go first of all to the top right picture, so we have here this hot reservoir and heat travelling in from the hot reservoir to the working fluid. And so you can see the working fluid here actually is shown as red molecules. And so actually the working fluid here is depicted as being actually at the same temperature as the hot reservoir. So the heat that's coming in from the hot reservoir, it's not actually increasing the temperature of the gas, but heat is going in and causing the gas to expand. And again, with the hot reservoir and the gas being at the same temperature, again you could model this as being sort of quasi-static, that's to say extremely slow, rather like a process that's effectively at equilibrium. And so the energy that comes in from the hot reservoir keeps the gas is at the same temperature, so-called isothermal, but the energy gets converted into work, and this is the piston moving up. So the piston is working against the external atmosphere in this so-called isothermal expansion, which is being powered by energy from the hot reservoir. So this is the first stage here of our cycle. And then into stage 2, what happens here is we somehow isolate thermally our working fluid from the hot and the cold reservoir. And so now there's no heat flowing between the reservoirs in this stage. This is what adiabatic means. It's thermally isolated. And what happens is this hot gas, which is initially at the temperature of the hot reservoir, the gas is going to expand just by virtue of the energy of the particles. And so as the particles do work, pushing the piston back against the atmosphere, that work comes, as it were, at the expense of the internal energy of the gas. And so the gas is going to cool down. And so we're going to get more expansion, but this is adiabatic expansion. So the energy provided, the energy that's being given to this expansion, coming from the gas itself. And so the gas cools in the process. So again, in this sort of idealized system, the gas is going to expand until it's cooled to the temperature of the cold reservoir. So it's converting the internal thermal energy of the gas to mechanical work. And that's going to set us up for stage 3. And so now we're going to move on to the next stage, stage 3. And so you can see in this, so we're ultimately going to return to how we were at the very beginning. You can see that in this stage, in stage 3, the gas is going to be compressed. You can see the arrow at the top, the compression, and it's so-called isothermal compression. Now, of course, normally when we compress a gas, we heat up the gas in practice. So, for example, if you're pumping up a bicycle tyre, you can feel the tip of the pump getting very hot as you compress the gas. So we typically associate compressing gases, doing work on the gases as heating them up. But in this idealized case, the work that we do on the gas, that energy is actually going to transfer into the cold reservoir. And so we can see using this symbol Q sub C, this is Q for heat, and this is heat going into the cold reservoir. So the idea is we're going to return the piston back into its original state. We're compressing the piston down. We're doing work, if you like, the atmosphere is doing work on the gas, and ultimately we're keeping the gas at the same temperature and we're moving the heat into the cold reservoir. So there we go, that's stage 3. And then finally what we're going to do is this so-called adiabatic compression. So remember, adiabatic means that the system is thermally insulated. So we're not having heat moving into or out of either of the reservoirs. And so what we're going to do is we're going to compress the gas a bit further, and ultimately we're going to heat up the gas in the process as we compress it, and ultimately this compression is going to heat up the gas to the point it gets to the same temperature as the hot reservoir. So effectively in this final adiabatic stage we're returning it to the very beginning where it's going to be in thermal contact with the hot reservoir. So these 4 stages take our working fluid around this kind of theoretical cycle, and at the end it's got back to where it was at the beginning. And so in fact we can represent this on a pressure volume diagram. And so on the pressure volume diagram that you can see, then you can see that these curves here, which are labelled T1 and T2 on the right hand side, the T1 and T2 curves, they're known as isotherms because this represents the gas at a particular temperature. And so we've got a high temperature and a low temperature state of the gas. T1 is up higher temperature than T2 lower down. And so actually the 4 stages that we've been through we can represent as the 4 sides of this sort of quadrilateral there between the 2 isotherms. So remember, our stage 1 was the heat entering from the hot reservoir isothermally, and so you can see there on the picture the wiggly red line, red representing the hot reservoir, Q representing heat. So heat has come into the system, but the system has remained on the same isotherm. So this is the so-called isothermal expansion. So you can see as the system moves between 1 and 2 on the diagram, you can see there that its volume is increasing. Its volume is increasing, but it's staying at the same temperature. On the other hand, when you go between points 2 and 3 on this quadrilateral, there's no heat entering or leaving the system. So this is a so-called adiabatic process. And this is where the gas was expanding. So you can see the volume goes up still. But the volume goes up, it expands, it does work on expansion, but at the expense of the own internal energy of the gas. And that's why the temperature drops between T1, the upper isotherm, down to T2, the lower isotherm. Then you can see the next stage, going from 3 to 4, the system remains on the same T2 line. So this is isothermal compression this time. Compression because the volume is going down. And so as work is done on the gas, you can see here that heat is leaving the gas. You can see the blue line there indicating that heat is going into the cold reservoir, and that's our Q2. So you see the T1 and the T2, these 2 extremes of temperature, these are the temperatures of the hot and cold reservoirs. And so the final stage here, going from point 4 to point 1, so again the volume's going down, it's an adiabatic step, there's no heat being transferred, and so as the piston is compressed, it heats up and it moves up from the cold temperature T2 to the hot temperature T1. And so another point about this is that if you're really thinking about efficiency, ultimately the most efficient processes are carried out reversibly. And so this is sometimes called quasi-static which means very, very slow. So it's kind of, to a best approximation at any moment, kind of resembling an equilibrium. And of course, under equilibrium conditions, we see that the entropy isn't increasing. And so making these systems change very, very, very slowly is the way we can minimize the increase in entropy. And this was actually the approach that Carnot took, this kind of idealized state where everything kind of is a bit like an equilibrium at any given time. And so this next point here, again, just refers to the heat exchanges with the reservoir. Q1, the energy coming in from the hot reservoir, and Q2, the energy going out to the cold reservoir. So because the heat is changing in the form of Q1 and Q2, the entropy must be changing. And of course, as Clausius defined it, the entropy change is going to be Q over T. And so with Q1, heat is going in, so it's like a positive Q, and so the entropy is going up. And in Q2, the heat is leaving the system, and so that would be a negative entropy from the point of view of the system. By the system, I mean the working fluid, because of course that heat is then entering the cold reservoir, but we're just focusing on the system itself losing that energy. So we've got a gain in entropy going from 1 to 2, and then we've got a loss of entropy going from 3 to 4. And so those other two stages, the two adiabatic stages, don't involve any heat exchange with the reservoirs. So if there's no heat entering or leaving the system, then by definition those entropy changes are zero. And so ultimately the work that's being done in these stages is going to depend on the temperatures that they're moving between, the hot and cold temperature. And so I'm going to generate here a slightly kind of hand-waving argument that's going to try and justify the conclusion I'm coming to. In fact, later on we can try and do this more rigorously. But for the time being, I'm just going to try and persuade you that the work done is only going to depend on the temperature ratios T1 and T2 in the cycle. And of course T1 and T2, these two temperatures are common to both of the adiabatic stages. So I'm going to be saying then that the amount of work involved is equal, or equal and opposite in those two stages. And so if we consider all of the stages where heat enters or leaves the system to be done under reversible conditions, in this kind of idealized way, then we can start considering the limit under these conditions of there being no overall entropy change. So we're treating as a kind of equilibrium these isothermal steps, and we know that there's no heat entering or leaving the system in the adiabatic processes, so they're certainly not going to contribute to the entropy. And so under these most ideal conditions, so no one's really pretending that this is going to happen in real life, but as a kind of thought experiment, the absolute limit of efficiency we can possibly have would be where a complete revolution of the cycle would give no overall entropy change, as a kind of theoretical ideal. Then we can look at the work involved in these heat exchange stages. So if we're going to say that there's zero entropy change overall, then it means we're going to equate the magnitudes of the entropy gain and the entropy loss of the two stages where we do see heat being exchanged. So we've got the Q1 over T1, that's the entropy of the system increasing in the first stage, and the Q2 over the T2, where the entropy change is going to decrease in the isothermal compression. And if we're going to say that the overall entropy change of the whole cycle is zero, then these two stages where the entropy changes, they're going to have to be equal and opposite, so they sum to zero. And so that's expressed here. And so I've actually been a bit neglectful of the signs, so I suppose here I'm really concentrating on the magnitudes. So I suppose you could argue that Q1 and Q2 should have different signs because one is heat going in and one is heat leaving, but I just want to concentrate on the magnitudes being equal here. And so as we come up to here in this third point, ultimately the work involved in stages where the heat is exchanging with the reservoirs is going to depend on the pressure and the volume of the gas. And in fact, one thing we can see here is that if you take the units of pressure, so I mean pressure is measured in pascals, isn't it? So that's force per unit area, newtons per meter squared. And if you multiply that by the units of volume, meter cubed, if you multiply those both together, you get newtons times meters, and newtons times meters is in fact the units of work. So you can see here that pressure multiplied by volume is something that's, dimensionally at least equivalent to work. So this gives you the kind of pressure volume connection here to the work. And so again, using this idea of the symmetry of the system and the ideal conditions, hopefully it's not too big a leap to appreciate that ultimately the ratios of the volumes are going to be equal for the two stages as well. And since pressure is proportional to temperature at constant volume, this is going to lead us to this result. Q1 over Q2 is T1 over T2. So again, we're disregarding the signs here of Q1 and Q2 and just considering the magnitudes. And in fact, this is something we can go back and prove later on more rigorously. It's just a bit more difficult mathematically to do it absolutely rigorously. Here is just kind of a justification. And so here we've got these ratios between the two quantities of heat energy involved being equal to the two temperatures involved for the two reservoirs. And now to look finally at the efficiency. And so what we need to do, we need to consider a complete loop of the cycle to represent this whole process. And let's look at it in terms of energy. Now, the only processes which change a form of energy from one type into another involve heat and work. And so we can see that we have Q1 heat going into the system and Q2 heat leaving the system. And the Q1 going in is going to be larger than the Q2 going out, as we established that the heat is proportional to the temperature. And so by conservation of energy, the difference in energy between the amount of heat going into the system and the amount of heat leaving the system must be equal to the work that the system will do overall. And it's this that we use in the calculation of the efficiency. So we're defining efficiency here, which we're using this Greek letter eta for, as the overall work done as a fraction of the heat energy that's been given from the hot reservoir. So this Q1, it comes in from the hot reservoir. So, it would be nice if all that energy that comes in could be converted to work. But as we see, this doesn't happen. Some of that heat remains as heat as it leaves the system, but the remainder gets converted into work. And so we need to find out what that fraction is. And so here's the expression here. So you can see that the numerator, Q1 minus Q2, the difference between the heat entering and the heat leaving, this on the numerator is the work that the system does overall in one loop. And so we're going to express that work as a fraction of the total heat entering from the hot reservoir. That's the Q1. And so just rearranging that, so you see obviously Q1 over Q1 gives us the 1. It's 1 minus Q2 over Q1. And since we've established that the Q's are proportional to the T's that they correspond to, we can replace Q2 over Q1 by T2 over T1. And so this efficiency here, this is going to be a number between 0 and 1. And so you can see here that T2 is the colder temperature. So you can see that if the system were to be perfectly efficient, then eta would equal 1. And for that to be the case, we would need T2 to be 0. But of course the temperature T2 is measured in Kelvin. So that would mean you'd have to have absolute 0 as the cold sink. And so this is entirely impractical. And so this is why you could never get 100% efficiency. And so the crucial point here is that the efficiency is related just to the temperature differences in this model, and that in practice you're never going to reach 100%. So even if all these things we're assuming, like we can treat the gas as an ideal gas, we can treat all the changes like they're quasi-static equilibrium-like changes, all of these ideas, unrealistic though they are, they still don't give you 100% efficiency. Then the efficiency is limited by the temperature difference. And so this kind of comes back to an earlier point we alluded to. it relates to the quality of the energy. So heat is a very kind of disorganized, low quality form of energy. All the particles are just bouncing around in a kind of random, disorganized way. And what we're trying to do is we're trying to convert that low quality energy heat into high quality energy mechanical work. So this is actually moving something against a force. So mechanical work is, if you like, the most ordered, if you like, high quality form of energy. And so it's perhaps, not intuitively all that surprising that starting off with really low quality energy, you can't 100% convert it to high quality energy. We can get some high quality mechanical work out of low quality heat through our heat engines, but it's never going to be a 100% conversion. And now a couple of questions for you to think about. So in this first question, we've got a couple of simple calculations, calculating some entropy changes. And so we're going to use the definition of an entropy change here. Delta S, so delta, that's that Greek triangular looking symbol there. Delta S, S for entropy, the change in entropy, equals Q, that's the heat change, divided by T, the temperature. So we've got heat measured in joules, as it's a form of energy, and the temperature in Kelvin K. This is absolute temperature, where 0 on this scale is absolute 0 in temperature, which is minus 273 degrees C. So one thing I should say is that this equation, you see we've only got one value of T in this equation, so we're assuming that actually the temperature isn't going to change. And since we're making that assumption, you can see in the calculations I've actually given very small quantities of heat in comparison to the amount of water being heated, so we're assuming the temperature is going to stay constant. That's a more difficult calculation otherwise. And then in number 2, we're working out a maximum possible efficiency of an engine, and so I'm giving you the temperatures here in Kelvin to make life a bit easier. And so I've got some round numbers here, so 2000 Kelvin, that might be the kind of temperature that could be reached in a modern engine. And as the exhaust leaves the engine, we're going to treat the cold sink to be the atmosphere at room temperature, so we're taking that to be a nice round number there, 300 Kelvin for you.